Chapter 4, Lecture 3, General Second-Order Systems. Using the definitions, the general second-order system can be written as follows, where omega n is known as the natural frequency and chi is known as the damping ratio. The general response of the system depends on the chi value. So if chi is 0, then that's an undamped system, and you'll have two poles shown as follows, at j omega n and minus j omega n. If chi is between 0 and 1, that's an underdamped system, and the two poles will be located off of both axes, as shown in the following diagram. And they'll be located at the following positions: j omega n square root of 1 minus chi squared, and then the negative version of that same value. If chi is equal to 1, that's a critically damped system, and the two poles will lay on top of each other. If chi is greater than 1, that's an overdamped system, and you'll have two poles that lay on the real axis in the S-plane. Let's see how this works. Let's given the following transfer function, let's see if we can find the natural frequency and the damping ratio. So we can compare this transfer function to the general form. We can see that omega n is squared is 36, so omega n has to be 6. And since we know omega n now, we know that 4.2 equals 2 chi times omega n. We can solve for chi, the damping ratio, and we find it's 0.35. So what kind of system is this? It's a underdamped system. We can also use MATLAB to solve this, and I'll show you on the diagram on the right how to use MATLAB to find the same values for omega and for the zeta value. I don't know if this is zeta or chi. I call it both depending on what day it is. So continuing this, once we have the zeta value and the omega, we can calculate the pole position simply by using the following functions. And so here on the left, I use MATLAB to find this value for the poles S1 and S2. MATLAB can also plot the poles and the step response. And so here you see how to do this in MATLAB, and I would encourage you to do this in MATLAB to plot this. So if you input a step response to this transfer function, you can see what the response is. And here you can see the two poles plotted on the pole zero map. So MATLAB has great power to calculate all these kinds of things, and it really depends on getting in and playing around with it. But use this code as your example when you're working through the homework and trying to solve for these, plotting the pole zero map and plotting the step response.